ladies and gentlemen, in this video we are going to discuss some typical problems from a written examination in chemistry. In this slide you can see a sample ticket which includes 10 problems, and we are going to discuss these problems one by one. Let's go to the first one. In the first one, one has to write the complete ground state electron configuration of element number 15. How do we do that? As the atomic number of the element is 15, it's obvious that this atom has got 15 electrons. Now we have to put these electrons into the electronic subshells of the atom. The building up principle says that electrons successfully fill electronic subshells in the following order. First, 1s orbital, then 2s orbital, then 2p orbitals, then 3s orbital, 3p orbitals, 4s orbital, and so on. As this element obviously belongs to the third period of the periodic table, we can stop here, and we're not interested in the order after 4s orbital. Each s subshell has got 1 orbital, and each p subshell has got 3 orbitals. And again, according to the building up principle, a maximum of 2 electrons can only be placed in 1 orbital. And we have to place them with opposite spins because according to the Pauli's exclusion principle, no 2 electrons in the atom can have the same 4 quantum numbers, and therefore their spin quantum numbers should be different, should have the opposite values, so plus 1 second and minus 1/2. So we put 2 electrons in the 1s orbital, we put 2 electrons into the 2s orbital, then we put 2 orbitals in each 2 electrons into each orbital of the 2p subshell, and that makes 10 electrons. Then we place 2 electrons into the 3s orbital, and then we have 3 electrons left, and we are coming to the most interesting part of this problem. According to the Hund's rule, the lowest energy atomic state is the one that maximizes the total spin quantum numbers for the total spin quantum number for the electrons in the open subshell. In this case, the open subshell is the 3p subshell, and we place first we place 1 electron into each orbital, and as we have only 3 electrons left, that will be it for this problem. If we had more electrons, we would have to put them here, so we would have to pair the electrons, but in this case we don't need to. And the electronic configuration of the atom in the ground state is this one: 1s2, 2s2, 2p6, 3s2, and 3p3. Now we have finished this problem. Let's go to the next one. Here we have to find out how many moles of ions are present in 2 liters of 0.5 molar calcium chloride solution, and we have to write the dissociation equation. First, we find the number of moles of calcium chloride in the solution, which is quite simple. We multiply the volume of the solution by the molar concentration of calcium chloride. 2 liters we multiply by 0.5 moles per liter, and we get 1 mole. So that means that 1 mole of calcium chloride is present in this solution, in these 2 liters of the solution. Now we have to decide how many ions will be produced when calcium chloride dissociates in water. Here is the dissociation equation. 1 mole of calcium chloride produces 1 mole of calcium 2+ ions and 2 moles of chloride ions. That makes 3 moles of ions from 1 mole of calcium chloride. Therefore, we have to multiply the number of moles of calcium chloride by 3, and we will get 3 moles of ions in this solution. So that was pretty simple. Let's go to the next one. Calculate the mass of 10 liters of argon under normal conditions. Well, the most tricky part of this problem is to remember what the term normal conditions means. it has been defined as a temperature of 273.15 kelvins, so which is 0 centigrade, an absolute pressure of exactly 100,000 pascals, not 1 atmosphere. Do not confuse it with normal temperature and pressure, which is defined as 20 centigrades or 293.15 kelvins, and an absolute pressure of 1 atmosphere. So you can see that, well, in these two cases, the pressure is slightly different. Yeah? Here we have 100,000 pascals, and here we have 100.1 kilopascals. And they're very, very close to each other, but not the same. Okay, now we know what temperature and pressure we should use, and it becomes simple, yeah. According to the ideal gas law, or Mendeleev-Clapeyron equation, as we call it in Russia, the number of moles in 10 liters of argon can be found as follows. We multiply the pressure by the volume occupied by the argon and divide it by the universal gas constant multiplied with the absolute temperature. And when we know the number of moles of argon, we will simply get the mass of argon when we multiply the number of moles by its molar mass, which is 39.9 grams per mole. And here are the calculations. Yeah? We multiply the pressure by the volume, by the molar mass of argon, and divide it by the pressure multiplied with the, not the pressure, by the universal gas constant multiplied with the temperature. And we get the answer of 18 grams. Here we just give 2 digits in the answer because we have only 2 significant digits in the data we have at the beginning of solving this problem. Okay, now number 4. How much water should be added to 250 grams of 60% aqueous nitric acid to obtain 20% solution? Okay, the mass fraction of any substance, any solution, can be calculated as follows. We divide the mass of this substance by the total mass of the solution, and then we multiply the number we get by 100%. So this will be applicable to any mass fraction that we calculate. So the mass of the nitric acid in the initial solution can be found from this expression. We can find it by multiplying the total mass of the initial solution, which is 250 grams, by the mass fraction of HNO3 in this solution, which is 60%, and by dividing it by 100%. And we'll get 150 grams. This is the mass of the nitric acid in the solution. The change in the mass fraction of the nitric acid is only due to the addition of water, because the nitric acid itself is neither extracted nor added to the solution. So it will still be 150 grams in the final solution. Its mass fraction can again be expressed as the mass of the nitric acid divided by the mass of the final solution multiplied by 100%, and therefore the mass of the final solution can easily be found. We multiply the mass of the nitric acid, which is 150 grams, by 100% and divide it by 20%, which is the mass fraction of the nitric acid in the final solution, and we get 750 grams. Finally, we subtract the mass of the initial solution from the mass of the final solution, and we find out that 500 grams of water should be added to the solution. Again, as only 3 digits are given here, we give 3 digits in the answer only. Okay. Write the molecular and ionic equations of aluminum chloride hydrolysis. And we also will have to find the answer whether the solution will be acidic, neutral, or basic. When dissolved in water, aluminum chloride dissociates to give 1 mole of aluminum ions and 3 moles of chloride ions, yeah, according to this equation. Chloride does not hydrolyze because it's the conjugate base of a strong hydrochloric acid. But aluminum ion forms a relatively weak base, aluminum hydroxide, and it hydrolyzes. In the solution, aluminum is surrounded by 6 molecules of water and forms this ion. And in this ion protonates water and loses one of the proton. Oops, sorry. Loses one of these one of the protons of water molecules surrounding it. Yeah, and this ion is formed, and the water molecule is protonated. As water molecule is protonated, it increases the concentration of H3O plus ions in the solution, and this solution will be acidic, of course. And here is the molecular equation for the hydrolysis of aluminum chloride. Aluminum chloride hydrolyzes to give basic aluminum chloride and hydrochloric acid. Okay, problem number 6. We have to write the equation for the reaction of copper with nitric acid. First, we determine the, also we have to know the oxidizer and the reductant, and we have to balance the equation by electronic balance method. To do that, we have to determine the oxidation number of each atom of the reactants and the products. The oxidation number of copper is 0, and the oxidation number, the most interesting oxidation number for us here is the oxidation number of nitrogen, which is +5. So we can see that copper will increase its oxidation number, being a metallic element, and nitrogen has the highest oxidation possible, well, for nitrogen, and it will decrease its oxidation number in this reaction. Depending on the concentration of the nitric acid, it can be reduced to nitrogen dioxide or to nitrogen monoxide, but this only happens when diluted aqueous solution of HNO3 applied. As this is quite rare, we will just consider the formation of nitrogen dioxide in this case. So the oxidation number of copper in copper nitrate is +2, and the oxidation number of nitrogen copper nitrate is still +5, so it doesn't change in this case. Then the oxidation number of nitrogen in nitrogen dioxide is +4, and the oxidation numbers of hydrogen and oxygen do not change at all. So we just write the elements changing their oxidation numbers. Copper changes from 0 to +2, and in order to do this, copper loses 2 electrons. And to change its oxidation number from +5 to +4, nitrogen adds 1 electron. We have to cancel the electrons when we add the first line to the second line, so we have to multiply the second line by 2. And this is what we get in the end. These coefficients will help us to balance the final reaction equation. So we can see that the coefficient between copper is 1 and is 1 here. So we just do not write anything in front of copper and copper nitrate. Here, in front of nitrogen, we have this coefficient. It should be 2. And as nitrogen has not changed its oxidation number here, we have to put this coefficient in front of NO2. Yeah, and we also have to consider that two nitrogen atoms do not change their oxidation number, so we have to put 2 plus 2 here, so that will make 4 in this case. And well, as we have 4 hydrogen atoms on the left, we will have to add the coefficient in front of water as well, and this is the equation we will get in the end. It is balanced. It is the equation that is expected as the answer for this problem. Number 7. We have to illustrate amphoteric properties of zinc oxide by several reaction equations. Well, as we know, amphoteric substances, well, substances that show amphoteric properties can react with both acids and bases. And so we have to write the reaction equations of zinc oxide with some acids and some bases. Well, I've taken just 2 most commonly used acids, hydrochloric acid and sulfuric acid, and they react with zinc oxide according to these equations. Zinc oxide dissolves in hydrochloric acid to give zinc dichloride and water, and it also dissolves in sulfuric acid to give zinc sulfate and water as well, and it dissolves in alkalis to give soluble zincates. For example, it dissolves in sodium hydroxide in presence of water, so in aqueous solutions of sodium hydroxide to give this complex zincate. Yeah, so we can see that it reacts with both acids and bases. So this illustrates its amphoteric properties. Number 8, we have to draw structural formula of all possible isomers of cyclopentane. First of all, we have to decide which classes of carbon, well, to which classes this substance can belong. Yeah, it can belong to cycloalkanes or to alkanes because it has twice the number of well, the number of hydrogen is twice the number of carbons. And to structurize the answer we get in this problem, we will first consider cycloalkanes with 5, then with 4, then with 3 carbons in the cycle. Yeah? The only possible formula with 5 carbons in the cycle is cyclopentane, so it's quite simple. Then we reduce the number of carbons in the cycle and make it 4. So there is 1 exocyclic carbon, this is methyl cyclobutane. And then we reduce the number of carbon in the cycle still more by 1. And that leaves us 2 exocyclic carbon atoms. Well, we can place them next to each other, or we can say that we can draw a structure with both carbon atoms attached to 1 carbon in the cycle. So it will be 1,1-dimethyl cyclopropane, and we can also attach them successively 1 by 1 to 1 carbon atom, and this will be ethyl cyclopropane. And for this structure, well, several stereoisomers are possible. Yeah? So these 2 structures are enantiomers with respect to each other, and well, this structure is diaster, or this structure is diasteromeric to both this structure and this structure. Now let's go to alkenes. Well, again, we have to structurize our answers somehow. And first we write all the structures with 5 carbon atoms in the chain. And here in the second line, we write the structures with 4 carbon atoms in the chain. First, let's consider the first line. Well, in both these, in all these structures, there are 5 carbons in the chain without any substituents. But in this structure, the double bond is between the first and the second carbon atoms. And in this structure, in both these structures, the double bond is between the second and the third carbon atoms. Yeah, here as well, between the second and the third carbon atoms. So the difference between them is that these they are stereoisomers, and this is the Z. This one has the Z configuration, and this one, sorry, this one has the E configuration, and this one has the Z configuration. So they are EZ, or otherwise cis-trans isomers to each other. Now we consider the alkenes with 4 carbon atoms in the chain. So this is the main chain, and we attach 1 carbon atom to the second carbon atom of the chain, and here we attach the carbon one methyl to the third carbon atom in the chain. We have to start from here, from this side, because the atoms bearing the double bond should get the smallest numbers possible. So it will be carbon number 1, carbon number 2, carbon number 3, carbon number 4, and here as well. And what is the difference between these structures and this structure? Here the double bond is terminal, so between the first and the second carbon atoms, and in this case, double bond is between the second and the third carbon atoms. Now we have discussed all 13 isomers possible for this molecular formula. Okay, now let's go to the next one, number 9. A sample of primary alcohol weighing 37 grams was oxidized to give 44 grams of monobasic carboxylic acid. We have to draw all possible structures of the reaction product. So the general reaction scheme will be the following one. And we can see that the molecular formulas of the reactant and the product differ by 2 hydrogen atoms and 1 oxygen atom. Okay, so the molar mass of the alcohol, if it's X grams per mole, then the molar mass of the acid will be X plus 16, because 1 oxygen atom is added, and minus 2 multiplied by 1.0, because 1.0 gram per mole is the molar mass of hydrogen, and 2 hydrogen are taken from the molecule. Yeah, and so the molar mass of the acid will be X plus 14 grams per mole. And if the yield in this reaction is 100%, which we have to accept, because otherwise we cannot solve this problem, the number of moles of the alcohol and the acid will be the same. So 1 mole of alcohol is oxidized to 1 mole of acid. As we know, we find the number of moles by dividing the mass of the substance by its molar mass. And we have both masses of the alcohol and the carboxylic acid, And we also have defined the molar masses of the alcohol and the carboxylic acid. It's X in case of the alcohol and X plus 14 in case of the acid. And as their number of moles are the same, we can have this proportion. And solving this equation, we will find out that X equals 74, which suggests that this formula for the alcohol can be rewritten like this. So in this formula, R is propyl in this case. For the alcohol, the formula is like this, and this is the formula of the acid. Yeah? And the possible structure formula of the acid are these two. The first one has got 4 carbon atoms in the chain, and the second one has got just 3 carbon atoms in the chain, and the 4th carbon atom is attached to the second carbon in the chain. So we have solved that one. Let's go to the last one. The product of the reaction of 10.8 grams of aluminum with excess of carbon was dissolved in excess of aqueous hydrochloric acid. What are the products of these reactions? And we have to calculate the masses of all reaction products. Well, first of all, aluminum reacts with carbon by this equation. Since aluminum is the limiting reactant, and the amount of aluminum carbide produced in the reaction can be calculated as follows. According to this equation, the number of moles of aluminum carbide is the number of moles of aluminum reactant divided by 4, and it will be 0.1 mole. Aluminum carbide reacts with hydrochloric acid with formation of methane and aluminum chloride, according to this equation. Yeah? Again, aluminum carbide reacts with excess of HCl. So the number of moles of methane and the number of moles of aluminum chloride can be calculated from the number of moles of aluminum carbide formed in the previous reaction. We have to multiply the number of moles of aluminum carbide by 4, to find out the number of moles of aluminum chloride, and we also have to multiply the number of moles of aluminum carbide by 3 to find out the number of moles of methane. It will be 0.3 moles. And well, all that is left to us is to convert the amount of these substances to their masses by multiplying the number of moles we have got for both of them by their molecular masses, molar masses actually. So in case of aluminum chloride, it's 144 grams per mole. In case of methane, it's 16 grams per mole. And here are the masses of both aluminum chloride and methane. So we have discussed all 10 problems of the simple examination test, and I hope it was helpful, and I wish you good luck in your examinations. Thanks for watching.